Hey all, my name is Ben from OP Labs, and this is a short session to walk through some of the high-level components of the OP Stack's fault-proof alpha. Over the past few months, we've been working to bring Canon and the OP program into 2023, creating the dispute protocol and implementing the off-chain challenge agent. We're all really excited to share the alpha release of this software with the community and get started on the next iteration. To be explicit, this system is not yet production ready. However, the core components of the proving mechanism are complete, and we are able to dispute claims about the state of L2 successfully. So today, we'll primarily be walking through the high-level components and talking how they fit together. So first, we're going to be walking through the dispute game primitive, what it is, and how we can build a protocol on top of it. And then we'll dive more deeply into the components such as the smart contracts, Canon and the OP program, and the OP challenger. So to start off, a dispute game is just a simple state machine. The state machine is initialized with a 32-byte root claim about any piece of information, and it also contains an abstract method to resolve the claim to be true or false. The dispute game can only exist in one of three states, so it can be in progress, which means that the root claim has not yet been determined to be true or false, challenger wins, which means the root claim is false, defender wins, which means the root claim is true. As you can probably tell, by itself, the dispute game is not very useful. All it does is describe the interface for a very simple dispute mechanism. It does, however, offer a high-level abstraction for us to build a protocol of multiple more complex disputes on top of. So we've built a protocol for registering and creating various types of disputes on-chain on top of this primitive. The core facilitator of this protocol is the dispute game factory contract. It's a minimal clones with immutable args proxy factory that keeps track of multiple implementations of the iDispute game interface. And whenever a new dispute needs to be made, an off-chain actor will begin by providing the setup data for the dispute, as well as the type of dispute game they'd like to create this contract with. With the dispute game factory, we're able to register and create various implementations of the iDispute game interface. So our first contribution to this protocol is the fault dispute game. However, in the future, we can create multiple different types of dispute games, such as one that's backed by a validity proof, an attestation dispute game, etc., etc. And once we have enough, we can also create a meta dispute game that aggregates the results of others and plug it directly into any bridge or other piece of smart contract software that currently utilizes the dispute game to determine the validity of claims. So the fault dispute game, as we just talked about, is our first contribution to this protocol. It allows for participants to bisect over an execution trace from a fault-proof program ran in the local emulator, such as Canon or Asterisk, in order to determine if the root claim about the state of L2 is correct. The game is played as one would expect over a binary tree, given that it's a bisection game. However, the internal game state is modeled as a DAG to allow for multiple claims to exist at the same position. This prevents an attack vector wherever a dishonest claim is countered by the same party who made the dishonest claim in a 1v1 game, allowing for deadlock or incorrect resolution to be forced. Once we reach the most granular level of bisection in this game, which is the leaf nodes of the tree, participants will be forced to execute a single instruction step on-chain via the fault dispute game's backend VM in order to prove their counterparty incorrect. The game is generic over the VM to support multiple fault-proof programs and emulators in the future, and for our implementation, which is backed by Canon and the OP program, the VM is a single on-chain MIPS thread context. So to understand more about how the game is actually played, it's really useful to look at a visualization. So here we have a game played over a mock VM used for testing called the alphabet VM. And the state transition function is very simple. Given a letter, it basically just gives you the next one. So for example, if you give it A, it'll spit out B. This has the advantage of having a much shorter instruction trace. Canon and MIPS instruction traces are a couple billion instructions long. So here we can visualize a game that's played over only a 16 instruction long trace. So to begin with, the root claim is made committing to the final trace instruction. Each node within this tree can be converted to one of these trace instructions at the bottom by running right until we reach the bottom level of the leaf nodes, and then pulling its index at depth. So the root claim commits to the entirety of the instruction trace at 15, and the only opportunity to begin bisection is to provide a midpoint. So the opening move of a game, if you believe that a root claim is wrong, is always an attack. And so that's what this challenger has done here. They provided their state hash at instruction 7, which is if you run down 2 and get to the bottom, 2 commits to instruction 7 in this tree. Going forward, the player counters this attack against the root claim by basically providing the next level of bisection. So because they disagreed with this hash, it means that they disagreed with this challenger's state at instruction number 7, and therefore they continue bisection by providing the next midpoint at 4, which commits to 3. So another thing can happen here, which is a defense move. So here what happened is that the challenger that made 2 actually agrees with the root claim's state at instruction number 3. But because this claim supports the root claim, they know that they must continue bisection. So this is the high end of the binary search, where we agree with the hash, but know that we need to continue bisection. And so we jump into the right subtree and find the next layer of bisection, which is the midway point of 5. And that is also at instruction 5. So the next move is a very important one, which is where we reach the leaf node of the tree. So the blue player responds back with another attack, which means that their instruction traces diverge in the state transition from 4 to 5. So the yellow player only has one option against this blue player now that we've reached the most granular level of bisection. As you notice, these are all individual instructions, and we can no longer commit to a large range. So we have to execute a single instruction step on chain in order to prove the above claim wrong. So here, the yellow player has come in and they were able to counter the blue player with an actual instruction step on chain, determining that the commitments to the state that they have been providing is wrong and resolving back up to 1. So once all moves have been made and the chess clocks have been ran out, the game is ready to be resolved. Effectively, each node in this game is the root of its own subgame, and a subgame is a DAG with a depth of 1. So here we can see that 1 is its own subgame, it has 2 as a response countering it, and 2 is its own subgame with no responses. A subgame is only countered if one of its responses is uncountered. So here we can see that 2 has no responses, and therefore it's uncountered. And because 2 is uncountered, 1 is countered. And so this root claim would be proven incorrect by 2. And this property percolates upwards. If we can imagine a game that was more played out, for example, if we bisected all the way down to instruction number 7, we would percolate that status of countered upwards all the way back up to the root. Each subgame can have multiple responses within it. The only thing that is required for a subgame root to be marked as countered is for one of its responses to be marked as uncountered. And so while this game is played over a mock VM that commits to the state of the alphabet at any given instruction, the same principle also applies for a fault-proof program, just with a heavier backend. So while the fault-proof programs game obviously exists on a tree with a much larger depth to support a larger instruction trace, the same principles do apply, and this instruction step will simply consult the on-chain MIPS thread context or whatever other VM is backing it, rather than the mock alphabet game that we're showing here for these tests. So now that we've gained some intuition around the on-chain infrastructure that allows us to resolve these disputes in an interactive fault proof, we do need to talk about the backend that actually makes this all possible. So Canon is an on-chain MIPS instruction emulator that was originally written by GeoHot a couple of years ago. As described before, Canon is actually what enables us to execute a single instruction step of an emulated Geth state transition on-chain to verify the correctness of a claim made about the state of L2 in this dispute game. So the classic idiom is that it's Go code that runs an EVM, emulating a MIPS machine, running compiled Go code that runs an EVM. And that's definitely a mouthful, so we'll break that down going forward. Canon does consist of the two main components, the binary itself, which is used to emulate the OP program and generate witness data for claims made within the fault dispute game by the off-chain actors such as the OP challenger. We also have the smart contracts, which consist of MIPS, which is a single MIPS thread context implemented in Solidity, and the preimage oracle, which is a contract that stores global and game-specific Keshack preimages for use in the thread context execution. The preimage oracle is also generic, so we hope that in the future this can be used by other VM emulators implemented in Solidity. So going deeper, the OP program is the fault-proof program that runs through the roll-up state transition to verify an L2 output from L1 inputs. The output of this program is ultimately what is disputed on chain, and Canon is simply an emulator that runs this code. So the program is designed such that it can be ran completely deterministically. So the same input data should always result in the same output. And because it's fully deterministic, it can be ran on-chain in the MIPS thread context as part of the dispute resolution process. So the easiest way to think about the OP program is that it is a lightweight state transition code from OP Geth, as well as the derivation pipeline, compiled down to MIPS, and that's ultimately ran on top of our emulator, which is either the Canon binary or the on-chain MIPS thread context described before. So moving forward, to give an intuition around how the components of the alpha fit together, we've got a little bit of a flow chart here. As a note, the system is deployed as a sidecar to the main system at the moment on Goerli. So in other words, it's currently only watching the system and not actually influencing which withdrawals are allowed to go through the bridge, etc. So here, kind of the core driver of this entire dispute process is the off-chain challenge agent, which is the OP challenger. It'll listen to outputs coming into the L2 output oracle on-chain, and if it detects fault, it'll initiate the process to create a dispute game. So whenever it detects fault, it will first run Canon over the blocks that are trying to be disputed. Canon will consult the OP program and actually emulate it, and the OP program will reach out to the preimage server for storing and caching preimages as well as fetching them if it needs them. Once the actual state commitment has been made, the OP challenger will call the dispute game factory to create a new fault dispute game. Once the fault dispute game is initiated, bisection begins to occur, and the OP challenger will effectively watch the fault dispute game as new claims come in and determine if there are any moves that it needs to make. Once we've actually reached that most granular level of bisection, as we were discussing earlier, the fault dispute game will execute a single instruction on-chain via the MIPS thread context. And the MIPS thread context may or may not need a preimage during its execution, and so we have a custom syscall implemented that allows it to reach out to the preimage oracle for data. And so once the instruction step is finished, the MIPS thread context will hand its result back to the fault dispute game. It will perform some comparisons to determine whether the state transition was correct, and ultimately resolve that subgame. So that about covers all of the high-level components of Optimism's fault-proof alpha system. So the alpha is currently deployed on the Goerli testnet. You can also find the addresses of the deployed system within the contract's Bedrock package in the Optimism monorepo, and you can also play with it on a local devnet and in the end-to-end tests. For security researchers and developers interested in interacting with the fault-proof alpha, we'll also quickly run through how to run some of the end-to-end tests for the system and also describe what's going on under the hood. For more in-depth documentation, definitely go look at the specs and the doc directories in the monorepo. We have some pretty well-written technical docs on many of these components that should help diving more deep into each of them. And so jumping into the monorepo, we can start to look at some of the end-to-end test examples of the full system running. So to find these, you guys can go into the OPED package and then specifically the fault-proof test file. And in this file, what you'll find is a lot of different tests running single, multiple dispute games with valid and invalid output routes, also with various backend VMs such as Canon, as well as the alphabet game. So today we're mostly interested in Canon tests, specifically because this is what the security researchers watching this video should be submitting their proof of concepts against if they find a bug. So today we'll look at test Canon dispute game, and we can run this in the background while we talk about it. So the first thing that this test does is define a couple of test cases in terms of where we want our instruction step to diverge. So following that, we run tests over each of these cases, and the first thing that we do is spin up the fault dispute game system. So here, effectively what we're doing is starting a couple in-memory clients, deploying some contracts, and getting the system in a ready-to-go state. After that, we start the Canon game, and effectively what this helper does is perform all of the on-chain interactions necessary for initializing the dispute game and getting it in a ready-to-play state by the challengers. So once this is complete, we programmatically start the honest challenger. This is the agent that will be consulting Canon as well as the honest L2 state to generate the correct state hashes and defend the correct state of L2 on L1. After that, we'll start a second mock challenger. This challenger will effectively do everything that it can to try to defend the invalid root claim. However, it'll always fail because the honest challenger will always be able to prove it wrong in the instruction step. So after both challengers have exhausted all of the moves that they could have made, we'll advance the time to a point that we can resolve the game, and once we get there, we'll wait for the game status to show that the challenger wins. So in every single one of these tests, the root claim has been incorrect, and therefore we can assume that with the presence of an honest challenger that has exhausted all of their moves, the game should always resolve in their favor. And so if we look at the actual test running here, we can verify this. So the root claim here is obviously incorrect. It's a hash with primarily 0 bytes in it. And so we can see that our honest challenger has come in here to challenge it on each opposite level. And so effectively what we can see is that the first attack was at position 2. As we expect, it commits to a very large trace index, and the honest challenger has provided the hash of the state inside of Canon at the given instruction step. And so we counter all the way down until we get to this final leaf claim that's made by the dishonest party. And note that the honest party was able to counter them through the instruction step on chain. And so this game will resolve to the root claim being false because there's not a single uncountered claim existing inside of the game state. And so this is just one of several examples of how we've tested the system. If you scroll down further in the file, you can see defense steps. You can see an invalid output route rather than a valid output route. And there are several helpers to help you guys put together tests to poke at the system and also to write neat proof of concepts for us to review if anybody finds a vulnerability in the system. So moving beyond the alpha, we can start to talk about what the plans for the future are. So going past this release, we have a number of plans for improving the system and fixing some of the aforementioned issues, as well as adding features in preparation for full integration with the production system. So the first thing that we're really targeting is adding an extra layer of bisection over output routes prior to beginning execution trace bisection. This is really important to enable the off-chain challenge agents to only need to run Canon over a single block rather than a string of blocks. This will also reduce the hardware cost of running the off-chain challenge agent, provide an upper bound on what Canon will have to execute, allowing for more sparse proposals on chains like the public goods network. Adding bonds to the system is also something that we'll have to do to preserve incentive compatibility. As you may have noticed in the alpha, defenses of the honest L2 state are not incentivized, which also means that attacks on the honest L2 state are not disincentivized. Adding bonds to each claim made in the game will preserve the incentives of the system as well as make it more costly to attack. The other thing is improving the dispute game's resolution algorithm to reduce the number of interactions that honest off-chain challenge agents need to have with the on-chain dispute game. This will reduce the cost of running the off-chain challenge agent, ensure that an honest challenger's participation always results in a profitable move for them, and it possibly prevent the need for challengers to respond to every invalid claim within the game. Finally, the fault-proof system will have to be taken out of Sidecar and integrated into the bridge contracts, specifically the Optimism portal, in order to make the system be able to be used in production, verify the correctness of output routes, and ultimately determine which withdrawals are allowed to go through. So that's about it for the Fault-Proof Alpha. We're really excited to keep continuing this project and bring it to a stage where it's ready for production. In this early stage of development, we definitely invite security researchers and developers alike to engage with the system. I definitely encourage people to look into the Immutify bounties that are available for any vulnerabilities found at this stage, technical documentation for developers to go in depth on some of the components that we spoke about today, as well as some of the CDMX presentations from earlier this year.